siblings, friends, fellow Earthlings, and dreamers of the dreams upon which we build our future. Welcome to Ask An Astrobiologist, the show that celebrates the science and the scientists involved in our quest to understand the nature of life. As usual, I am your host, Dr. Graham Lau, also known online as the Cosmobiologist, and we are brought to you by the NASA Astrobiology Program and SeganNet.org. Now, as always, before we start the show, we love just saying a huge shout out to all of you who are watching live, all of you who are watching later, the recorded version, all of you who interact with us across the interwebs and all the different social media places we can be found, just to share your ideas, to comment on the polls that we put out there, and to show how awesome our guests are. This month, we want to say a huge shout out to Johnny Time, that's at Space Nuke J, who said, Dr. Young's exoplanet biosignature work? Heck yes, June 17, locked in with the telescope emoji. Love it. That's fantastic, Johnny. Thank you so much for watching the show. Thank you to all of you for tuning in. Now, today's episode is going to take us to the early Earth and to modern Mars, to exoplanets far away, and to envisioning what the next generation of space telescopes may reveal in our quest to understand the nature of life. And all of that is because of our special guest, Dr. Amber Young. Dr. Young is a Pathways Research Assistant in the Planetary Systems Laboratory at NASA's Goddard Space Flight Center, where she studies exoplanets and models exoplanets that could exist and how we might look for them to see signs of life beyond Earth. She uses climate and photochemical models to investigate biosignature gases and chemical disequilibrium, these key clues that we have in looking for a possible terrestrial planet's signs of life in its atmosphere. Amber is also working on science strategies for the proposed Habitable Worlds Observatory, or HWO, which I have a hard time saying that sometimes, so I'm going to abbreviate to HWO from now on. She's also a former NASA Pathways Fellow, a first-gen college graduate, and a lifelong video gamer and crocheter who brings her creativity to the cosmos and to the search for life out there. Dr. Young, thank you so much for joining us for Ask an Astrobiologist.
Hi, Graham. Hi, everyone. To those who are watching, it's so great to be here. Thanks for having me.
Yeah, it's such a pleasure to have you. We're so excited to talk about all of your work, including all of your interests like video gaming and crocheting and all the other awesome things you've done. But I love to start with all of our guests first and just asking, what was your science origin story? What turned you into the superhero you are now and started you on this path towards becoming someone involved in modeling exoplanet atmospheres?
Well, my origin story definitely starts off from childhood. I've always been interested in astronomy and curious about that subject matter. I've watched so many different programs, like how the universe works, and I'd be the kid that would be sitting there, taking notes, trying to write down facts and learn as much as I can from those programs. And I remember in school, it was about sixth grade. I had this really amazing science teacher who, of course, there were different units. And so we would transition. Once we got to the astronomy unit, I was really excited about it. I was the kid in class that had answers to all the questions, knew the ordering of the planets, off the top of my head. And one day he pulled me aside after class and he says, you look and you seem really interested about this topic. What do you want to be when you grow up? And I looked at him and I said, I want to be an astronomer. I want to be a scientist. And, he said, that's amazing. That's wonderful. How do you feel about math? And when I looked at him about that question, I was like, oh, math, I don't know, not too good at it. I don't feel like I have as natural knack for math as I do with astronomy. So I don't know. And he said, well, in order to be a good scientist, your math foundations have to be really strong too. And so I took that advice to heart and, he started mentoring me from there on the rest of the school year in my math, helping me make sure my math foundation was strong. And it was kind of interesting because at the time, there were these national competitions that were called Math Olympiad. And my science teacher had encouraged me to sign up for Math Olympiad after months of, practicing with him and kind of going to him after school for tutoring sessions. And, I was intimidated by that. I said, how can I, do this competition and train for it? But I went ahead and I did it, and it was an amazing experience because it pushed me to feel more confident in my abilities and to really take the next steps to taking what I felt was a weakness about myself and keep pushing to improve it and to work on it and really, stare at those weaknesses and say, okay, well, what can I do to make it better? What can I do to keep on improving? So, the math challenges were great. Participating in Math Olympiad, while it was challenging and I never actually, won awards from doing it, it was still a really great learning experience. And it helped me practice math and think about math in new ways. So that was just an amazing experience. And I'll always have that sixth grade math teacher, or my science teacher, Mr. Franz, to, look back on and sort of cherish those memories. I also
That's awesome.
think that, a lot of part of it too was like my family just being supportive and wanting to see me pursue a career in this realm, just because, it's always been my passion, but I never knew anyone who worked at NASA, which has always been my dream job. And I never knew anybody who pursued science, as a career. So it was kind of like this dream that seemed out of reach, seemed like it's worlds away, but still kind of pushing for it and taking the next steps. And my parents always, giving me those opportunities to work toward that and support me through schooling and college, all of that.
That's fantastic. Well, I'm thankful to your family and to Mr. Franz for supporting you and helping you to build yourself into this career you've pursued. And from my understanding, from your undergraduate work to your master's degree work into your doctoral work, you kind of moved around a little bit in the topics of study from early Earth oxygen concentrations to understanding methane and chemical disequilibrium on modern Mars to then incorporating exoplanets. And so I'm wondering how you see this shift in your own research background and career impacting how you now think about the search for life out there.
Mhm. Yeah. So, for one, I didn't expect my research to kind of take those different twists and turns, which is nice. It's nice to not have your plan and set out and feel like you need to be strict and stuck to the same research question or the same problem. For me personally, when I first got started in research, it was in undergrad while I was still a student at Penn State and I was a junior. It was my first year at University Park campus. And I wanted to pursue research, but I also really wanted to learn how to code. For whatever reason, I kind of got exposed to that skill, and it seemed like it was, ubiquitously used throughout the sciences as a tool to be able to carry out research. And so I wanted to learn that more. And at the time, while I was working there as a student, I had met a graduate student at the time, Natasha Battaglia, who was already working in a research group. She was a NASA NSF GRFP fellow at the time, and she was pursuing her research at Goddard while also doing her graduate studies at Penn State. And I met her, and she was the first person that I ever met that was working at NASA, and I was like interacting with her on the day to day. And, I talked to her about my career aspirations. I talked to her about wanting to code and learning those skills. And she said, okay, then let's have you do research. Let's have you hit the ground running, and, kind of helped me sort of develop those skills and tools to pick up modeling, particularly atmospheric modeling, photochemical modeling, and climate modeling, which is what most of the work was being done in the research group that we were in. And so taking those skills of first learning Python, first learning how to code in the terminal, and then applying and translating those skills into the photochemical modeling and really applying those to these different problems, that sort of helped me develop the knack for taking those transferable skills and applying them to different questions, to different problems, which I love. I feel it's mentally stimulating. It's invigorating to tackle a new science question and a new research area. And, I find it to be helpful to be able to market those skills in a way that is always allowing me to adapt, always allowing me to kind of take the tools and the skill sets that I've learned and apply them to different problems.
I love that so much. And for a lot of our audience watching, they might be interested in pursuing careers in astrobiology or in astrophysics, physics, various realms of science to also be involved in this quest to understand what exoplanets could be like out there and what we're looking for alien life. And so maybe they want to learn more mathematics, more coding, but also modeling. There's a famous quote by George Box that all models are wrong, but some are useful. And so I wonder, in your own work, how have you developed models that we find useful in looking for life out there? What do we actually need to know for like the basic kinds of information we need to really build a model of an atmosphere?
Yeah, for one, I definitely stand by that motto. Heard it early on in my career as well, and it's really important to kind of take into account, the balancing act that exists with regard to modeling work. There's always going to be sort of high tech, high capable modeling efforts that maybe, for instance, for 3D GCM models, where you're sort of modeling the general circulation of Earth's atmosphere, its climate, and we know Earth so well. We have so much data revolving Earth that you can afford to do those high fidelity models, and you can afford that high level of detail. Whereas, say for an exoplanet, where much less is known, for one, and we have presumably much less data on a particular system. But then, on top of that, sort of balancing the challenge that, depending on the quality of data, what you're trying to observe, you may not be able to afford that high fidelity, high amounts of computation time to kind of dedicate it. So having a model that is both flexible enough and nimble enough to be applied to the questions that you're trying to ask is important, and sort of keeping in touch with, again, that balance between model fidelity and, what are sort of the challenges that you have to overcome, the model limitations by chance, if you're trying to take a model that was originally developed for this parameter space, but then you need to adapt it, or you want to apply it to a different parameter space, but then that requires adaptation. That requires, maybe removing inlaid assumptions or inlaid biases that may not be applicable for the parameter space you're trying to explore. So just kind of maintaining that balance is key, I think.
Yeah, absolutely. And I think, a lot of people, they hear these buzzwords like habitability of exoplanets and inhabited worlds that might be out there. And we think about the different kinds of factors that might matter in looking for, say, an Earth-like world out there. Now, certainly there could be life as we don't know it, or life that exists on other kinds of worlds. But I guess a fun question could be, how valuable is it for us to look for Earth-like worlds first?
Mhm. Right. So when I think about the approach for the search for life, and thinking about the strategies that we're implementing in a mission like HWO, what I love about it, for one, is that in the most recent Astrophysics 2020 Decadal Survey, they kind of made a call out to searching for life and using Earth through time as sort of a vehicle for being able to do that. And I stand by that approach, just, for one, because the decadal survey is community driven. It's based on our efforts and what we believe is the best strategy to take on to move forward. So, that's the community consensus, is that we should be doing this, and we should develop a mission that's capable of doing this. So being able to sort of stand by that and be a part of HWO, where that's sort of the goal, to first order is exciting. And another thing that I think about in terms of, searching for life and using Earth through time as a baseline for that, is just in the terms of, if you're sort of searching for life, what I try to think about, or kind of think of an analogy, is if you lose your keys, and you're searching for your keys. You have a few places of where you normally keep your keys. For me, it's in my purse, so that's probably be the first place that I'd look. If not there, then maybe on my kitchen counter, if I took them out by accident, I forgot to put them back where they were. And so just thinking through, kind of retracing your steps, thinking about what is the logical step. That's the approach that we're taking with the search for life, is like, well, the Earth that we have is the only known example for life. And so thinking about the approach to search for life, let's start with what we know. Let's start with developing and building a mission and observatory that's capable of being sensitive to life as we know it, so that hopefully, when we make the search, we'll know it when we see it, and we'll know that we've designed a mission that's capable of finding what the examples that we have to go off of. And another aspect to this that I really think is important in regards to searching for life is that, a lot of times when we think about the search for life and we're thinking about Earth, we're thinking about modern Earth. We're thinking about the Earth that we know of today and the life that exists today. But what's great is that there's a large wealth of information over Earth's geological history, and it has been inhabited for multiple epochs that have all been sort of unique and distinguished from each other. And so we can kind of use Earth as a mechanism for being able to explore different types of Earth and different ways in which life has expressed itself over this long, vast geologic timescales we have to work with. So.
Yeah, that's fantastic. In SegaNet's Astrobiology Revealed issue 11, which included an interview with yourself, you mentioned some work that you and your colleagues did last year on a paper that you published looking for Proterozoic Earth as a key target for looking for possible habitable Earth-like worlds out there. But you also mentioned some issues with looking for a Proterozoic-style Earth. And so I wonder for our audience, if you could just share, why would looking for something like a Proterozoic Earth be so important on all these different snapshots through time of our planet?
Yeah. So one reason why Proterozoic Earth has held sort of a near and dear place in my heart is because Proterozoic Earth does represent a very large fraction of Earth's history, about 50%. And so just based on the time scales that we're looking at, again, having an observatory that could be sensitive and be able to detect and characterize a type of planet that sort of represents and is indicative of a geological time period that was sort of well existed and has that longevity. We need not be subject to maybe a more serendipitous detection, which might be the case for modern Earth, just for the sheer fact that modern Earth hasn't had as much geologic time and as much of that time to really develop and hasn't existed for as long. So, just probing that question of the geologic time periods that have been extended and represent, that larger fraction of Earth's history to tap into, while also sort of looking at, biosignature detection for given species like oxygen and methane. What's great about Proterozoic Earth, and especially in terms of chemical disequilibrium approaches, is that, let me step back. Chemical disequilibrium is sort of looking at gas pairs, or you could be looking at gas pairs that you wouldn't expect those two species to be coexisting or present alongside one another. But maybe there's a biological process or a metabolism that's continuously replenishing that more volatile species. And so they always remain co-present. For Earth, that's oxygen and methane in terms of its atmosphere. And for Proterozoic Earth, that holds true as well. But we have an advantage in the sense that for Proterozoic Earth, there could have been more methane lingering around. So it sort of lends itself to being a little bit easier to detect, just because if there's more of it from a remote perspective, you might be able to characterize the chemical disequilibrium signatures a little bit more for that case study. And of course, it's still challenging. It's still difficult in terms of the signal to noise ratios that you would need. But still, that was kind of the premise, and the test bed was hey, Proterozoic Earth is kind of a lot like modern Earth. And we might be luckier in finding more Proterozoic Earth-like planets in comparison to modern Earth-like planets, given how long its history was. So let's dig into that, and let's look at chemical disequilibrium signatures for that particular era. And that's what that study was about.
Absolutely. That's awesome. I do want to step away just for a second from that and come back in just a moment. First, I want to share. So we were thinking of a poll that we could do with our audience to pull some of these ideas about what impacts habitability. And we could have certainly touched on all kinds of things like a stabilized obliquity from a large moon, or plate tectonics, or the origins, evolution of life changing an atmosphere. But we were curious just to toss out what kind of star or star type, stellar type, might impact habitability. We offered the audience choices of G-type stars like our sun, M dwarfs or red dwarfs, K-type stars, and white dwarfs. And K-type got a lot of love, but G-type definitely got the most by a large amount. Nearly 60% said G-type stars. But of those who actually made comments on our poll, two that we wanted to point out was that one from Carlos Fotografo or Carlos Snaps is that they are fascinated by these long-lived, stable K-type stars, and that they might be ideal for finding a universe teeming with life if there's life in those habitable regions around those stars. Zainab, who was a past Young Scientist Program participant at Blue Marble Space, she wrote that G-type stars are like the sun, so if I would choose, I would go with G-type, but the search for extraterrestrial life is more focused on K-type ones currently due to stability and long lifespan. And so I'm wondering, for you, Dr. Young, what is your take on this? I mean, your work so far is focused kind of on Earth-like worlds around G-type stars, but what do you think of K-type stars and these other possible stars for having habitable worlds around them?
Right. Yeah. So I think what's great is that, again, sort of standing by like Habitable Worlds Observatory, its development, part of its strategy is to be sensitive to the range and the gambit of sun-like stars. And so you could sort of outline and, kind of pick and choose and prioritize targets by, what's nearby, which target stars then make the cut in terms of being on the list. So definitely kind of categorizing and making sure that our sweep encompasses all these different stellar types is really important. And especially in terms of understanding the effects that the host star would have on the resulting chemistry of that planet. Whether or not you could drive even more amounts of methane or provoke, additional processes that could still be biologically driven, but again, it manifests itself differently. Is certainly interesting and important to kind of be sensitive to as well. And I think in a realm where whatever life is doing, if it's still able to kind of manifest and produce these remotely detectable signatures in the form of like stronger spectral features that are easy to characterize, easy to kind of, apply modeling techniques to kind of infer processes that could be going on, is definitely important. So, take on it.
Yeah. I mean, we've come so far in our understanding of geological processes, both on Earth and potentially beyond, that might lead to these larger systematic dynamics of disequilibria in atmospheres. There have been certainly many arguments about oxygen as a biosignature or not a biosignature, actually being like an anti-biosignature. And so there's been some issues, in really trying to constrain our models and better understand what we're looking for out there. And so I'm curious, Dr. Young, from your viewpoint, what are some of the key issues right now that we need to overcome maybe in the next decade or so in exoplanet science to help us improve the search for life out there?
Mm-hmm. Right. So again, sort of taking on a modeling perspective, I really think it's important to be able to continue pursuing and doing intermodal comparisons with one another. So there's a lot of different ways in which you can take a spectroscopic data set and then be able to apply modeling techniques to it, like retrievals, which is one of my specialties, to be able to infer information about that given data set. And so what we are currently stepping into is a new territory for exoplanet science, where now we've got this observational data for certain types of planets, the ones that we've been able to observe either, with JWST or other means. And so being able to apply models like retrievals, again, it's sort of new territory. We're all sort of biting off pieces of the puzzle to be able to do that. But I think taking a step back and sort of doing intermodal comparisons with each other and making sure that the techniques that we're implementing, potential biases that are inherently encoded in the models, but we don't necessarily see or predict it yet, is really important. And to contribute to that, to help with that, I've been sort of participating and a part of the cuisines modeling intercomparison framework. It's being run by Tamal Falche here at Goddard and a lot of other folks who are, taking models and taking different pieces of the modeling effort and just coming together and intercomparing their models to be able to both see, okay, where are they disparate? And then sort of outlining, okay, why are those disparities happening? Is it due to assumptions, or is it due to different data sets that we adopt as our sort of starting points? And so for me personally, I'm leading an effort that's called risotto. Like all the dishes, all the cuisines, intermodel comparisons, they all have different dishes, food dishes associated with them. And that's because the whole idea actually came about during a dinner over Thai food to do this intermodal comparison work. So I run risotto, and risotto is explicitly for intercomparing retrieval models in particular. So it's like retrieval intercomparative simulations of trailblazing exoplanet observations. And so we've been focusing on taking a variety of different exoplanet data sets, like simulated data of GG1214b, for instance, and just applying all of our individual retrieval models to those to that simulated data set and seeing, okay, how close are the results in terms of the retrieval results themselves, the posterior distributions that we get, the uncertainties that we get on specific parameters. And that's been really interesting to do because we found that at the core of every retrieval model, there has to be a forward model. And in our case, in terms of interpreting spectroscopic signals, radiative transfer is at the heart of that. And it turns out that, a lot of people do that differently. A lot of people adopt their own sort of data sets for, say, line lists and the spectroscopic absorbers, that information that you encode to be able to run your forward model. It can come from different places and can introduce differences in the modeling outputs. I know another exoplanet-driven modeling effort that's been done is also through the SAGs, the exoplanet organizations that are sort of looking at and exploring these different problems. And there's a particular SAG that's also looking at retrieval intercomparisons. It's led and run by Dr. Tyler Robinson and Dr. Renyu Hu. So, again, we're cross collaborating and we're moving toward those efforts. And I think just, continuing that front will help us, because when we outline those differences between our models, we're both improving, like we're both taking steps to kind of address sort of any pitfalls or any sort of limitations that exist. And it outlines that. It helps us sort of build those frameworks. And these are the tools that we're going to be using. Even, 10, 20 years down the road, they might manifest themselves and sort of evolve over time, of course. But to first order, we want to have our tools in place so that we know exactly, okay, when we get the data, when we are spoiled with a wealth of knowledge and data, how do we interpret it and how do we continue to sort of move the field forward? Because you can only interpret as much as you're able to kind of predict, and the model's, again, only as good as as it can be. So
yeah. And I love this idea of like collaborating and comparison of the different models that different people are using. All of science relies on collaboration. It's a foundational part of science, is to share our knowledge with each other. And so I'm also curious how you see your own role in empowering the next generation of researchers who will come after you, and how you see yourself as a mentor for guiding people who'll be doing this work in the future as well.
Mm-hmm. Yeah, that's a great question. Like, for one, mentorship has been a huge factor to being able to get to where I am today. If I didn't have folks like Mr. Franz or Natasha, or, Sean Domingo Goldman, who was my very first research advisor and, helped me attain and be in NASA for the very first time with an internship. Those mentors that I had really, impacted my career, impacted the types of problems that I was interested in. Because when you gain exposure to those experiences, then you really do have the opportunity to figure out what you like, what you don't like. And that was just instrumental for my career, is just having the opportunity to be in the space, to step in the space, contribute what I can, learn what I can. And so taking to heart what I have experienced and what had worked for me, those are the core values, and those are sort of the things that I would like to do as a scientist, providing opportunities, if it's in the form of bringing on research interns and sort of giving somebody the opportunity to work at NASA for the very first time and gain exposure to what sort of happens behind the curtain for someone who might have been dreaming about it, but has never, had the opportunity to explore it. Those are the opportunities that I want to be able to provide to, the younger generation, to new early career scientists, and sort of carry that on as, maybe in a way, carrying on the legacy of the mentors that helped me, is bringing in folks and helping folks who have that same drive and that same capability, but maybe, haven't been seen yet, haven't been discovered yet. And so I'm an early career person myself. And so this is what I aspire to do. This is what I am looking forward to do as I approach even just, mid to late stages of early career, moving into mid career, certainly.
Yeah, that's fantastic. I mean, I think often in my own work of how we empower and embolden the next generation to really take big steps in their own lives, in their own science and philosophy and their impacts in the world around them. My own child right now is very young, but for Father's Day, he bought me a Lego set of the Perseverance rover that we've been building together. And for me as a scientist, it's been good to have some escape using my hands to build this Lego set. I also love working in the kitchen. And so I understand that you also really love crocheting. And so I wonder if you can share for us, like how crocheting has impacted your life and given you something kind of adding some creative value in your own world.
Yeah, for sure, for sure. So when I started crochet, I haven't actually been doing it for very long. My husband, a couple years back, had gifted me the crochet Woobles starter kits. And so I started with Pierre, the penguin, and that was the very first time that I had ever learned how to crochet. And the videos were amazing because it was taking me through step by step and teaching me, how to do different types of stitches. And the project itself, it took me about 2 days to do the first one. But for me, that meant like instant gratification of like, hey, there's this thing that I made and it's finished and complete, without like extended amounts of time and effort to do like a huge project. It wasn't overwhelming at start. So I loved that. I loved that it was a skill that, my husband sort of gifted to me as a way to like take my eyes off of the computer screen and focus on something that was sort of physical and methodical. And I really enjoyed that aspect of being able to create something with my own hands, and the fact that every project that I did after the fact, I was able to, again, apply those skills, apply those sort of concepts to anything, like a single stitch in a circle. You can, make a sphere. You can keep going. You can increase your stitches and then decrease your stitches. And that concept applies to any small circular thing you want to make in terms of like the body of an animal. So I was just taking what I learned from Pierre, applying it to making bears, to making foxes, like just doing all these different types of small animals. And it really helped, again, with just being able to get that creative side out. Ask my friends and family, like, hey, what's your favorite animal? And they tell me, okay, I like dragons. Like, I want to do a dragon. And then I got to figure out, okay, where's the pattern that I can kind of learn from and make or adapt in order to create a dragon and, gift those small stuffed animals to my friends and family has been really fun. And another portion of this, in terms of taking it to the next level with doing like garments. So the very first garment that I ever made was a crocheted hat, a bucket hat. And the premise behind it was like, I have very voluminous hair but I love to wear hats. I only really wear hats when my hair is braided, but I would love to wear hats all the time if I could, but I can never find a hat that can fit over my beautiful afro. So I set out to try to make a hat that if it's custom sized and it's built by me, then I can wear it anytime. I can, make it a size that I want to make it. And so building and creating that bucket hat was like the first time where it felt like, hey, I'm taking this into my own hands and I'm making something that's custom for me that I can wear and use. And it was just fantastic. There was a lot to learn with regards to making garments in terms of blocking and, again, sizing, measurements. I knew I wanted to make a bucket hat, but there was no perfect pattern to follow. So it was taking YouTube videos from different content creators and putting all that knowledge together in order to make a bucket hat that would still follow the look that I was going for, but fit me. So it was a lot of learning curves and it was a lot of challenges to overcome in doing the project. And it took me way longer than the amigurumi stuffies that I am typically used to. So it was a huge breaking into that space, but it was really fun. And I love my little flowery bucket hat. I still wear it when I have my braids in, but when I do my space buns, I can also, wear my bucket hat on top and
Awesome.
use it.
That's so cool. So for the sake of time, I do have to move into the next segment. I could talk with you about your research and mentorship and your creative side all day, but I do want to get to our audience questions since I see a bunch of them coming in already. But first, we have our Faster Than Light segment. These are questions we ask every guest who comes on the show, and just like probing this range of different thoughts from a variety of astrobiologists who are working in our field. The very first question is one that I added because I think it's kind of cool. What is your favorite thing that life on Earth does?
Yeah, so I love the resiliency of life. We'd be hard pressed to find an area nowadays where life doesn't exist because it's just so, once it's there, once it gets its footholds, it can adapt, it can manifest and just be present everywhere. And we find it in the most unlikely of spaces. Hypersaline environments, extremophiles exist. And so it's just awe-inspiring to me how resilient life is and how prevalent it can be. Again, once it sort of takes its footholds, that sort of gives me hope that if life does exist out there, that it's also resilient and capable, and we'll be capable of sensing it because it is, kind of this life force that can persist in some of the most unlikeliest environments.
I love that. Yeah, life is very resilient, and there's so much about life on our own planet we don't know yet. So, if you could communicate with any non-human organism from Earth, what would it be, and what would you want to talk about?
Yeah, so it's kind of funny. If I could communicate with any animal, it would definitely be cats. And in particular, it would be my two cats. So my husband and I have two cats, Kiara and Orion, and they have such unique personalities and they are so complex little creatures. I know that they understand exactly what I'm saying when I'm, talking to Orion or kind of fussing at him, if he's scratching where he shouldn't be scratching or, just kind of interacting and, giving me that playful nature, that playful side of him. And so I would love to have a conversation with my cats. I'd love to be able to ask them, like, on the day to day, like, what are your biggest plans? What do you like about your life? What are tips? Can you teach me the ways of the cat? Because you look very happy and comfortable.
Yeah, I love that.
I need that.
I would definitely love to hear from my Huskies what they think of the life they live with not being walked often enough and not being given enough food. I'm sure they have comments to drop. So I know that you're also into video gaming. I love video games myself. They super inspired me a lot, as well as reading novels and stories growing up about space and astrobiology. What
Mhm.
stories have inspired you to want to know more about life in the universe?
Yeah. So I love that you brought up video gaming because one of my all-time games is Mass Effect, like just the whole trilogy. I can't even pick between the three because the storyline and the breadth of the worlds that they created, it's just so much to take in. And it inspired me because they put so much thought into each character, into the different races that exist within the universe, the alien races, and uh, it, the world building and the story you go through, sort of again persevering through challenges as Shepherd. I always pick female Shep, and so sort of taking on charge as the commander of your ship, the leader of your ship. It also sort of imparted like this confidence and being able to pick your storyline through your role playing allowed me to kind of impart some of myself into the character. Like, if I were to go the Paragon option and I want to be diplomatic, I want to lead my team with the same effectiveness and the same empathy that Shepard does. Um, it's just nice to be able to embody that in a video game and again, feel like, okay, these are the things that I kind of want to aspire to, and I kind of want to, and maybe not see myself on a spaceship, commanding a fleet of, a fleet of people, but just in terms of like research teams and stuff, like building into that. But Mass Effect was kind of a recent love for me and recent discovery also through my husband because it's the first person shooter game and I'm not typically good at first person shooter games. Like it's pretty intense, the fighting and the combat. And I'm more of a story type of girly. I like, the cozy game style of video games. So Mass Effect was a huge step for me in terms of engaging in the combat, but I got good at it and really enjoyed it. So that was also a really great milestone. But when I was a kid growing up, another story that I really loved were movies, sci-fi movies like Men in Black and Independence Day. Again, just the themes surrounding like alien creatures and having a breadth of different types that all existed and all, had their quirks. And, over time, Will Smith as an MIB personnel agent was like learning and communicating with these different species and really being the bridge between humans and other worlds. So I loved kind of seeing that dynamic. And Independence Day, Jeff Goldblum was absolutely brilliant. He embodied what I envision as a scientist in terms of thinking about your problem, thinking about your science 24/7 and being immersed in it. Um, so those are
Yeah.
some of the stories that really inspire me.
Love it. I just watched ID4 yesterday while making dinner. Such a good
Yes.
film. And Mass Effect is awesome for those who maybe haven't played it yet. The story is wonderful. I also am a story
Yeah.
person. I'm not big on the big multiplayer online gaming as much as I really love games with really good, deep stories. And Mass
Yeah.
Effect is incredible. I also usually play Paragon more than Renegade. I have a harder
Yeah.
time, just being a jerk to other characters in the game. But yeah, it really
Yeah.
is a beautiful story. And it places like a human future out there in the cosmos, meeting other beings. And so my next question for you could be, 10 years down the road or a century down the road or a millennium down the road. What is something that excites you about the future?
Yeah. Well, what really excites me is the prospects that we have sort of on the table with the mission efforts that we're working on, particularly in regards to the Habitable Worlds Observatory. It's not only a mission that I'm actively involved with and sort of focusing my research efforts toward, but the goals of the mission are what really resonate with me. Sort of taking on the age old question of are we alone in the universe and building an observatory capable of being able to at least start the seedlings of answering that question. Like we may not know for certain, but at least we go out and we search and we try and sort of funneling those efforts into building an observatory that could be on the same sort of technological scales as JWST in terms of overcoming and surmounting these challenges, it really excites me, because I think when we as a group, large teams of people, come together to solve problems that could very well be the most technical and rigorous challenges that humanity has ever faced, overcoming those has boundless effects and has sort of boundless advantages to the rest of the world, to the rest of the community for which we as civil servants are serving, fundamentally. And so sort of taking on something that's ambitious and really going for it in terms of overcoming these different observational challenges is really exciting, because I know it's going to sort of pay back in dividends the amount of knowledge and wealth that we as a community can take part in and celebrate. And that's something that's happening in real time with other missions like JWST, Hubble. These are the missions that are groundbreaking and are what we think of when we think of transformative science. And so if HWO can also be the conduit to that, and having a little piece of that is what really excites me.
Fantastical. Yeah. I love that so much. There's so much for our future. So I do have one more question in my Fast and Light segment, and it's kind of the favorite of most of our audience.
Yeah.
What is an unbelievable science fact that still blows your mind?
Yeah. So what still blows my mind is the fact that the surface temperature of Venus is hot enough to melt lead. Like, that is just crazy to me, because Venus is always thought of as, the sister planet to Earth. It's similar in size, and it only varies by a bit in terms of orbital distance, and yet it's still so fundamentally different from Earth. And having Venus as a planet that we can probe as another terrestrial planet that still has sort of evolved in time very differently from the way Earth has evolved gives us another advantage and test bed to be able to understand, okay, what is it that we could come to expect from planets that we might search for and find elsewhere in the cosmos. So Venus is always our humbler, in that we shouldn't always assume a Earth-sized planet is going to be the same as Earth, because we have an example of that right here in our backyard. And I know folks that I work with are also really involved with the Venus missions, with Da Vinci. And I know Stephen Kane, he's probably clapping if he's watching right now, because he's a huge Venus lover. But so I also share that love. And
Yeah, I'm with you and Stephen on that one. I think a lot of us wish Venus got more love just for more missions.
Yes.
And there's more science we need to do at Venus and on Venus. And so hopefully we'll see that soon. Now, Amber, I could speak with you for hours if we had time for it, but I do want to jump over to some audience questions, since a bunch of them are coming in, just to roll through a few of them in the little time that we have left. Before we even started speaking, Carmen Fregapane, I hope I'm pronouncing that correctly, jumped in the chat and said, given the problems that habitable zones orbiting M dwarfs are likely to face, do you feel that an enduring biosphere is most likely to develop on planets orbiting the mid-F through mid-K type stars?
Interesting. So I think that there's still a lot of work to be done in terms of exploring potential habitability around M dwarf stars. We only have few cases to draw from in terms of JWST data, and hopefully there will be future missions that kind of continue to push the envelope in terms of characterizing M dwarf planets in particular, understanding the star planet interaction and how that does sort of translate and affects potential habitability. What's great, though, in regards to being sensitive to sun-like stars and going at this with direct imaging, it just gives us the opportunity to kind of probe and empirically test, the habitable zone, the limits, and whether or not we can really sort of confirm and test those hypotheses of habitability. Is it the stellar environment, or is there more at play here in terms of planetary evolution and the evolution of a specific planetary scenario? Just being able to probe those different exoplanets and those environments is really important.
Yeah, it's extremely awesome and very important. I want to answer a question from Elizabeth Forbes Wallace quickly, just since Elizabeth asked what we meant by the George Box quote that all models are wrong, but some are useful. It's a really fun realm of the philosophy of science to explore, Elizabeth. This realm of do we understand objective truth? And the idea of a model, be it a mental model or perception of the world around us, the cosmos, or a mathematical model, it's built on assumptions, and it always has limits. And you might think back in the ancient past, we had various models as a civilization that, as we developed science over time, we've learned those models were wrong, and so we've built ever better models to explain the observations we have of the universe. But still, we're pretty sure most of our models, or all of our models, are wrong in some ways. And so can we ever actually build a perfect model is a fun question to take offline after the show and explore in the realms of the philosophy of science, the mathematics of the science. But for you, Dr. Young, a very fun question came in from Daryl Iverson. Daryl wants to know what a day in your work life looks like.
Oh, nice. A day in the life of Amber as a researcher. I start my day. I come in to Goddard. I work 5 days a week on center, and beginning parts of my day, I'll be the mundane tasks in terms of reading emails and whatnot. But the fun parts of my day that really start up are like the different collaborative meetings. Either groups that I lead, like Risotto, where we meet once a month, and I get to chat with like-minded retrieval modelers and really dig into the weeds of a particular problem or a particular challenge that we're all facing. And other meetings that I have. So just engaging in different collaborations that are ongoing right now. So one of them is an internal research project that I'm actually working with in collaboration with Mark Musa, who's an engineer, and approached me and my colleague Jada Arni about using machine learning algorithms and techniques to be applied to exoplanet spectra, and really opening the doorway to how will we look at habitable worlds data in practice. How will we go through each individual planetary case and sort of categorize it? We can do that effectively with machine learning. And Mark, wanted to take on that project to tackle it. So we've been working on that all year. And just a couple of weeks ago, we had 2 summer interns on board with us to work on the project. And so it's been such an amazing, wonderful experience to work with these graduate students. One of them is sort of my science grad student, Fasuda Trihan, who's a graduate student at the University of Albany. And it's just been great to kind of interface with the team and build on that project. So a lot of my day is going through emails, but also collaborating, meeting with folks, and a little bit of time in there for my own research work in terms of coding or writing papers. Fills up the bits in between.
That's awesome. Yeah. I think, everyone I've spoken to in this show, all the astrobiologists have different creative interests, different work days, but we're all approaching these kinds of problems and ideas in very similar ways. Now, another fun question came in from Elizabeth Forbes Wallace regarding the biases that we might have in our science. And Elizabeth asked of you, have you found it helpful to talk to people who are not astrobiologists, but who have the necessary scientific background to help shine a light on said biases?
Oh, yeah, absolutely. Absolutely. That's one of the things that I love about astrobiology is that it weaves together so many different subdisciplines. And no one person that at least I've met so far has had an answer to everything and every perspective. So, taking that collaborative approach to gaining perspectives from folks who are coming from biology, or even, in the case of my exoplanet machine learning project, working with folks coming from a perspective of computer science backgrounds and engineering in terms of developing the instruments to actually probe and test the science questions that we want. It all kind of folds together, and no one person can do or tackle it all. So I think in particular with regard to like modeling biases or assumptions, definitely we turn to folks for, say, in earth sciences with regards to, atmospheric models, and building a model that we can then translate to other parameter spaces. Maybe we will need help then from other planetary scientists if we want to translate a model to work with Titan. Okay, there's people in our lab that work on Titan and understand organic cases. So let's go to them and let's figure out how to make it happen. So definitely weaving in those different perspectives in order to mitigate those biases and also sort of transform and build on our modeling techniques is absolutely crucial.
Yeah, absolutely. And on the point of modeling, I have one more question. I apologize to everyone else who had all the amazing questions. We don't have time for all of them. But Anurup Mohanty, who is one of our production assistants, brought in a really interesting question that I think is really important for all of us right now. With AI, machine learning changing so much, this is the International Year of Quantum for quantum computing. Anurup asks, for the future of modeling, how do you see advances right now in AI and quantum computing shaping or even transforming the field of modeling?
Right. There are so many ways in which machine learning has been able to officiate our processes for data analysis, data reduction, and it's a realm that I've just kind of been exposed to and broken into myself in terms of learning the exposure, and learning how machine learning can really be applied. And so I'm sure that it's going to be a tool used and necessary going down the road, just because it's so nimble and flexible and can be applied to all these different challenges and problems, especially with regards to big data and sort of interpreting big data sets. So that's how I see it kind of evolving and sort of taking shape and certainly growing and continuing to be used.
Awesome. Well, maybe we'll have you back on Ask an Astrobiologist sometime in the near future to talk about how it's impacted things and changed your career and how your career is going with new discoveries awaiting us all the time. And hopefully with HWO coming down the pipeline, we may eventually have some observations to talk about as well. So Dr. Young, thank you so much for joining us for Ask an Astrobiologist.
Yeah, thank you guys so much for having me. Appreciate you all.
It's such a pleasure. And thank you to our audience, as always, for tuning in, for watching, for asking your questions live. As always, we can't get to all of the questions. We do our best as much as we can. So please reach out in all of the interwebs to ask further questions and interact with us and our guests. We love being here as a resource for all of you who have questions about our various realms of research in astrobiology. For those who want to stay in the loop on upcoming news about events, upcoming episodes of Ask an Astrobiologist, and more from NASA Astrobiology, you can sign up for the NASA Astrobiology mailing list. And so thank all of you for watching. Thank you, Dr. Amber Young, for being our special guest this month. Thanks again for joining, for watching in the future. And until next time, stay curious.